Okay, section 9.10, Taylor and Maclaurin series. The homework for this section is 5 through 39 odd. Now, in a previous section, we learned how to build Taylor and Maclaurin polynomials. And you may have noticed when you were doing that homework, if you did that homework, that sometimes you could see a pattern in the coefficients. And that's the whole deal that we're doing now. We're going to try to recognize patterns in the coefficients and write them as functions of n, so that they can so that we can take just a Taylor or Maclaurin polynomial and figure out how it behaves with respect to the counter. And remember that that a Maclaurin series is just a Taylor series that's centered at 0. So this is x minus 0 here. For the most part, we will be doing Maclaurin series unless it's something like the ln of x. You can't take the ln of 0. And in that case, we'll be offset a little bit, or we'll be looking at the ln of x plus 1 or something like that. Okay, our first example here, we are going to develop the Taylor series or Maclaurin series for the function sine of x. So the way you do this, you practiced finding your Taylor polynomials before. So you're going to need all of the derivatives, and this is going to go infinitely long, so we need to get enough of these derivatives that we start to see the pattern. And you see how we're popping back sine, cosine, all the way down. But we've got plus, plus, and then minus, minus, and then plus, plus. Because we're centered at 0 in a Maclaurin, we're going to then plug 0 in for each of these things. And now we see this pattern emerging where we have 0 for every other one, and plus 1, minus 1, plus 1, and we can predict that that's going to continue. So writing it out, remember that your formula is the nth derivative with your center point, x minus your center point to the nth power over n factorial. So that's where we're headed. And now in the blue here, these are the terms, right? This is the 0 term, the first term, the second term, like that. Those are the n values. Once we write out all of our terms here, you see that where n is even, we are 0. And that will continue forever because of just the nature of the sine function. And then when n is odd, we have a particular pattern where we have 1s here, 3s here, 5s here, and we see that it's all the odd numbers, and it matches the n value. But what we need to do is rewrite this thing so that we start at 0 and we have each of our counters is a non-zero term. So what I want to do is for this first non-zero term, I'm going to start with a new n starting at 0. The second non-zero term is 1, the third is 2, like that, because we're starting at 0. So now let's look at some relationships. If my n is 1 and I need 3's, what can I do? I can multiply it by 3, right? But then when n is 2, I need 5. So just multiples of multiplying by 3 isn't going to work. So I need to find a different relationship that works for every single term. So I tried 2 times this plus 1 gives me this. Double this is 4 plus 1 gives me 5. Double this plus 1 gives me 7. And you see this pattern all the way through. And even when n is 0, if I double it and add 1, I get the 1 for the power and the 1 factorial in the denominator, which is just not, you don't even look at it. So I have a new way of writing my a sub n. A sub n is going to be plus or minus 1, minus 1 to some power over 2n plus 1 factorial in the denominator. And now let's look at the power that n needs to, that the negative 1 has to have. When I'm at 0, I'm positive. When n is 1, I'm negative. So it seems to me that raising the minus to the power of n is going to work. When it's squared, it's positive. When it's cubed, it's negative. Do you see how that works? So we're going to make that minus 1 to the n. And so we take what we found to be our coefficient and we rewrite it. This is a sub n x to the power. And it just turns out the power and the denominator are both the 2n plus 1. That gives us only odd numbers. But now we're plugging in a 1, a 0, a 1, a 2, a 3 like that and getting just these non-zero terms. So we have created a power series or an infinite series that represents the sine function. Thing we need to know though is where is this convergent? So we almost always use the ratio test, and especially because you see there's a factorial here. Sometimes the factorials will cancel out when you do the processing that we just did. In this case, they don't. So we're just going to do a ratio test. So I have my power series with ignoring the minus 1 because it's absolute value. So I have my guy in the bottom, and then I'm going to add 1 to these n's for the top. But notice that both of these n's are being multiplied by 2. So when I say n plus 1 right here, it's really 2n plus 2 plus the 1 that's already there. So in the top, both of these are 2n plus 3. Let me write that out. 2, I changed the n to n plus 1, and you see that that comes out to be 2n plus 2 plus 1 more. So that's why those guys turned out to be what they were. And now I flip the bottom, multiply. This x, there's 2 more x's up here than there are here, so we end up with x squared. And hopefully you've practiced this enough that you recognize that 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So this can cancel all but the 2n plus 1 part up here, and we're left with those two factors in the denominator. Now, when we take the limit as n goes to infinity, you see we have n squared in the denominator and no n's in the numerator. So that limit goes to 0, which is always less than 1. And you see that this has no dependence on what x is. It's always 0. 0 is always less than 1. That means that our interval is our radius is infinite, and our interval goes from minus 1 to minus infinity to plus infinity. Okay, let's try the same thing for cosine. Remember the sine was all odds, right? Odd powers of x, it was alternating, and we had odd number factorials in the denominator. But watch what happens when we have the cosine. So we take all the derivatives, you see the pattern, cosine, sine, it's always going to be that way. And anytime we take the derivative of cosine, we have a sign change, an SIG change, but not when we take the derivative of sine to get cosine. So we have a plus, and then we have 2 minuses and 2 pluses, and we'll have 2 minuses and 2 pluses forever and always, amen. Now we're finding the Maclaurin, that means C equals 0. Sorry about that. C equals 0. So we plug in the 0 for these x's. Cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1, but now it's negative, and then I get a 0, and then I get a plus, and then I get a 0, and then I'll get a negative 1 0, positive 1, 0. So you see how these terms have zeros in between, just like the sign did, right? So let's look at the pattern. My ends, my original ends were the 0, this was 1, this was 2, this was 3, 4, 5, 6, 7. You get the point, right? So we need a new counter that's going to ignore the zeros and only give us what we need, right? So we want this to be the 0 term. Well, that's x to the 0 divided by 0 factorial, right? 0 factorial is defined as 1, right? Okay, this guy right here, if his counter is 1, then these two guys are twice the counter. Let's see if that holds. If this counter is 2, these two values are twice the counter. These are doubles, so you see that our power and our factorial are all just twice my counter. All right, what about the minus though? We started with plus, minus, plus, minus. So when the power on negative 1 is 0, we get a positive. When the power of negative 1 is odd, we get a negative. Even, plus, odd, minus. Even, plus, and on and on and on. So we have just the minus 1 to the n. So the point of all this is, once you create your series, your polynomial, you find the pattern that corresponds with the counter of the non-zero terms, and you can write that as a function of your counter, and then you can write it as an infinite series representation of the function that you started with. Now, you always have to check your interval of convergence. So we take the x to the 2n over 2n factorial, and we do the ratio test. We almost always do the ratio test. And remember, the ratio test says that your series converges if your limit is less than 1, not less than or equal to, less than 1. So we do our deal. Here's the thing. Here's the next term. It's just like the last one. Invert the bottom and multiply. You have 2 more x's in the top than you have in the bottom, so they cancel. You're left with the x squared. And when you write out this factorial as 2n plus 2 times 2n plus 1 times 2n factorial, that guy cancels, and you're left with those two guys. Take the limit, you get infinity squared in your denominator, which is going to make the whole thing go to 0 no matter what x is. Therefore, this thing has a radius of convergence that is infinite. And we go minus infinity on one side of 0, minus infinity on the other, and we get that this thing is convergent for all values of x. Okay, what if we have cosine or sine or some other basic function that we found a power series representation for, but now there's something happening to it. In this case, let's say our cosine is cubed. So we know that the power series for the cosine is this right here, and we know it's convergent everywhere. So all we're going to do is take this thing that's being raised to the, this thing that's being raised to the 2n power and change it from plain old x to x cubed. Do you see that? And now x cubed to the 2n is going to give me x to the 6n. And that's as simple as it gets. Sometimes you'll have numbers. If that had been 3x squared, we would have plugged a 3x squared in here, and the 3 would have been to the 2n power, and the x squared would have been to the 2n power, and we would have gotten whatever that was there. Okay, another basic function, plain old e to the x. Anytime we take its derivative, we just get the same guy. Anytime we plug zeros in, we get ones. This is a very cool power series, and you see that this gets expanded like this. You see for your counters, 0, 1, 2, 3. The powers and the factorials are matching our counter. Easy enough to do. We have x to the power on the top and then the counterfactorial on the bottom. Do the ratio test for this, and you'll see that this converges from minus infinity to plus infinity. Now, let's mix it up a little bit. Once we know our power series for e to the x is just x to the n over n factorial, now we have e to the function. We're just going to replace that x with this function. And you see that, well, let me write this down. We've got 4 times the sum from 0 of something to the n over n factorial, and the something that we have is 3x squared. So we're going to end up with the 3 is raised to the nth power, and the x squared is raised to the nth power. That gives us x to the 2n. Very quickly doing the ratio test, we have our guy in the bottom. We've got 1 added to all the n's in the top. Notice that when I add 1 to this n, the 2 distributes and I get 2n plus 2, which leaves me with an x squared in the numerator. And this factorial is n plus 1 times n factorial. We just peeled the first factor off and canceled all of the rest of them. We're left with this in the bottom. That makes our limit go to 0 no matter what x is, and this guy converges everywhere.